What I want to talk about in this short segment is the idea of guards. It's another way of writing a conditional in Haskell, and it's the method that people prefer. So when you're writing a definition, you can say, here are the alternatives at the top level of the definition by describing a sequence of cases where each case is guarded by a Boolean expression. Let's look at a concrete example to make sense of this. I'm defining a function that takes 3 integers and returns an integer. And it tells us how many of those 3 things are equal. So it could be all 3 are equal, in which case the answer is 3. It could be that just 2 of them are equal, in which case the answer is 2. It could be they're all different, in which case the answer is 0. Now that's an informal description. What you can see here is a Haskell definition of that. And it says there are 3 cases, and the expressions between the vertical bar and the equals are guards. They are Boolean expressions. And this says if the first guard is true, the answer is 3. Only if the first one is false do we look at the second. So we only say that the second only holds if the first doesn't apply, and then we check to see whether that holds. So we're looking at the case where we know all 3 are not equal, but it may be that 2 are equal. So that's how we describe the answer there. And then finally, we have a case which catches all the other cases and otherwise. So that definition pretty much reflects exactly what I said informally. Let's just run through this with an evaluation by hand. Here you can see we're in the drawing palette, and I've included the definition here. Let's run through an example where we apply how many equal, I'll just write H, to 4, 1 and 4. So what we have to do first is check the first guard, and that says is 4 equal to 1 and 1 equal to 4. Now we can check each of those is true. Each of those is false, and so we have false and false, which is false. So we check the next condition, which says is 4 equal to 1, or 1 equal to 4, or 4 equal to 4. Now these evaluate respectively to false or true, and false or true is true. So we're getting the result true here, so we use the corresponding expression which says the answer is 2. When I do these evaluations by hand, it's not that I'm trying to describe something that is complex, but what I want to show you is that it's always the case, whatever we define in Haskell, that we can do this. What we're doing when we evaluate, when we run something, is that we are simply doing this evaluation which we can repeat by hand. It's the sort of calculation we learned to do at primary school, and that's what we're doing again here. Admittedly, in a more complicated situation with more complicated data, but we are simply using the definitions we have to give us the results of that evaluation. Let's go back to the slides. So here we see the definition, and what a general definition with guards looks like is this, that we have a name of a function, we have the parameters to the function, and then we have a number of guards, and corresponding to each of those is a collection of results. So we can have as many guards as we wish. Remember, they are read sequentially. We can include an otherwise if we wish. It's not mandatory, but it's good practice always to include an otherwise. It's just worth saying that we don't have to use guards. We could use if then else to give us the same effect. But I think you'll agree that the definition you see at the top, it's clearer what's going on. You've got these three cases, you go through them in sequence, and the first one that gives you a true result, you see the corresponding expression guarded on the right hand side. So that's what I wanted to say about guards in Haskell.